Now that we can analyze circuits containing op-amps, let's take a look at some applications for these types of circuits. I'll start out by reviewing the rules governing ideal operational amplifiers, since it's these properties that make op-amps so useful. We're using three rules to model their behavior. First, the currents into the input terminals are both zero. Second, the voltage difference between the input terminals is zero. And finally, the output voltage is constrained to be within the range of these external voltage supplies. The rest of this video will cover some applications of operational amplifiers. To understand these applications, you have to keep these rules in mind. There are two categories of applications I'll discuss in this video. One important application is isolation of different parts of a circuit from one another. A common example of this is in instrumentation systems, where some physical parameter is being measured. In many cases, sensors used to measure this parameter may produce the necessary voltage, but don't have the power necessary to transmit or record the signal. Okay.
All right, from the top. Whenever you're ready.
There are two categories of applications I'll discuss in this video. One important application is isolation of different parts of a circuit from one another. A common example of this is in instrumentation systems, where some physical parameter is being measured. In many cases, the sensors used to measure the parameter may produce the necessary voltage, but they don't have the power necessary to transmit or record the signal. Op-amp circuits are a common choice to increase the power output from a sensor. Another example is the implementation of mathematical operations. When I introduced systems and block diagrams, I talked about reducing a complicated problem to basic components. These components consisted of simple mathematical operations. One of my examples was an addition process, indicated by this block diagram. Another example of a mathematical process was multiplication by a constant, as shown here. In this video, I'll introduce circuits that perform both of these mathematical operations. After that, I'll talk about a common circuit that's used to isolate different parts of a circuit from one another. My first example of a mathematical operation that's implemented by a circuit is multiplication by a constant. This circuit was analyzed in a previous video, where we found that the output voltage was equal to the input voltage times the negative of the ratio of RF to RN. As a block diagram, the input-output relationship for this circuit can be expressed as shown here. The output equals the input times a negative constant. This particular circuit is called an inverting voltage amplifier. The input and output are both voltages, and the output equals the input multiplied by a number. Scaling by a constant is commonly called amplification, so this circuit is amplifying a voltage to get another voltage. The inverting designation refers to the fact that the sign is changed between the input and the output. It's important to realize that our model of the previous circuit as performing multiplication by a negative constant is not completely correct. Remember that the output voltage is restricted to the range specified by the external voltage supplies. If the output voltage tries to exceed this range, the output becomes limited. This limiting process is called saturation, and it's a nonlinear effect. In our example, the output is equal to the negative of a constant times the input voltage. If we plot the output voltage as a function of input voltage, we get a curve that looks like this. For small values of Vn, this relationship holds, and the plot of output versus input looks like a straight line with a negative slope. If the input voltage is increased beyond a certain value, though, the rails limit the output voltage and the amplifier saturates. The slope of the line in this range is just negative k. In this range, superposition holds and the system operation is linear. However, when saturation occurs, the system response is no longer linear. Changing the input in this range no longer changes the output. For my next example, let's look at a circuit that performs an addition process. In this circuit, I have two inputs, V1 and V2, and one output. All the resistance values are the same. Now let's analyze the circuit to determine the input-output relationship. This terminal is connected directly to ground, so it's 0 volts. The op-amp says that these two voltages are the same, so this is also 0 volts. If I call this node A and do KCL at A, the sum of this current plus that current is equal to 0. So this is 0 minus V1 over R plus 0 minus V2 over R plus 0 minus V out over R. That sums to 0 because there's no current into the input terminals. If I multiply through by R, these all cancel out. Taking V out to the other side, V out is the negative of V1 plus V2. This circuit is called an inverting summing circuit. The output's the sum of two input voltages, and the negative sign corresponds to inversion. As a block diagram, this circuit could be indicated this way. The output is the negative of V1 plus the negative of V2. Next, let's take a look at a circuit that's commonly used to isolate different parts of a circuit from one another. This is about the simplest possible op-amp circuit. The input voltage is applied at the non-inverting input terminal. The output voltage is fed back directly to the inverting input terminal. Let's write an input-output equation for this circuit. The input voltage is saying that this voltage is Vn. The op-amp says these two voltages are the same, so this is also Vn. There's no voltage difference between this terminal and this terminal, so V out is equal to Vn. The output voltage is simply the same as the input voltage. The circuit doesn't really seem to be doing anything. However, this circuit is useful enough to have its own name. It's called a voltage follower. Next, I'll look at why this circuit can be useful. The circuit of our previous example seems fairly useless. It's a lot of work to go to just to get your input voltage back. However, this circuit can perform an extremely useful task. It can isolate different parts of a circuit from each other. For an ideal operational amplifier, the current out of this input voltage source is 0. That means that the input voltage source isn't providing any power to the circuit. The current provided at the output terminals comes from the external power supplies rather than the power source. Now let's look at a case where a voltage follower might be helpful. We have a design task to provide 6 volts to a load resistor. Unfortunately, we have only a 12-volt source available to us. A first try at the design could be to use a voltage divider. If we put 2 resistors with the same resistance in series across a 12-volt source, the voltage across either individual resistor will be 6 volts. However, if we hook up our load resistor to one of these resistors, we don't actually get the 6 volts across the resistor that we want. For this example, if our voltage divider is composed of 2 100 ohm resistors and our load is also a 100 ohm resistor, this is the resulting circuit. Unfortunately, these resistors are no longer in series and we don't have a voltage divider. There is a non-zero current to the load resistor. If I combine these two to an equivalent 50 ohm resistor, then the voltage here will be 1/3 of 12 volts or 4 volts. However, that doesn't mean that our original idea of a voltage divider is completely without merit. We just need to keep any current from flowing to the load. We can isolate the load from our voltage divider by putting a voltage follower between the two like this. Now the current here is 0, and these resistors are back to being in series. So this voltage is 6 volts. The op-amp supplies the current to the load resistor, so the load resistor voltage is also 6 volts as long as we can treat this op-amp as being ideal. Operational amplifiers are often analyzed as dependent sources. Now that we have a way to implement dependent sources, we'll spend some time talking about analyzing circuits containing dependent sources.